My name is Nico Sommerdijk. I'm a professor in bone biochemistry in Radboud University Medical Center. In 2019, we established a new electron microscopy center in Radboud UMC, where we provide services for our colleagues from within Radboud University Medical Center, from outside, also from colleagues from industry. And we're bringing together really advanced electron microscopy techniques to push beyond the limits of what currently we're able to do. And one of the ways that we're doing that is the use of liquid phase electron microscopy. In liquid phase electron microscopy, we were, as it were, putting our samples inside a little aquarium so that we can see the processes in the microscope while they're ongoing. The microscopes have vacuum, and the aquarium prevents the sample from drying out in the microscope. The aquariums have electron transparent windows so that we can actually see what is happening inside. But the problem is that the electron microscope uses a concentrated electron beam that is not only giving us information, but is also damaging the sample. So we have to be very careful in how much electrons that we can use. The more we use, the clearer the images are, but also the less images we can record, because every image is damaging our sample. So what we want to do is to reduce the damage, and we want to reduce the number of electrons that we needed. And that is how we ended up working together with SenseAI, who have developed a methodology where we can use only 20% or 10% of the pixels, and therefore of the electrons that we're using, to create an image in which originally you don't see much, but after processing, after filling in the missing spots, basically, you reconstruct back the image as it were. And if we compare these images with the ground truth, so basically images that have been fully recorded, it's very, very difficult to see the difference. This is how we think we can reduce the electron dose that we need, a factor 5, maybe factor 10, so that we can actually record more images or get better resolution in the images that we're recording.
My name is Luca Rutte. I'm a postdoc in the group of Nico Sommerdijk and also part of the Electron Microscopy Center. My research focuses on the development of workflows to enable the imaging of dynamic biological processes using liquid phase electron microscopy. My own research focuses on biomineralization, where we encapsulate pieces of tissue and we simulate the process of bone growth. As Nico already mentioned, these processes are very sensitive to the electron beam. So the subsampling helps us to reduce the damage on our samples. So at the moment, we are using 20% subsampling, and we confirmed that the reconstructions are identical to the original by comparing it to the fully sampled images. We also saw that we do not have a reduction in the resolution while we subsampling. So one additional challenge in imaging biological processes is that you need a large volume to look at the process. We are now able to reduce the electron dose in this thick volume to 1 electron per square angstrom, with still reaching a resolution of 5 nanometer using STEM.
More recently, we have started a project where the mineralization of other tissues is being investigated, specifically where you do not want it. We're looking now currently at heart valve calcification, where the collagen of our heart valves also becomes mineralized for reasons that we still do not very much understand. Now, there we have really a crazy project planned. What we want to do is to, at the moment that we think some interesting things are happening, we're taking sample that we freeze at the moment that we think, okay, now is a good moment. Then we take out a lift out. So we're using a focused ion beam scanning electron microscope to make a lamella that we take out, and we take that to the TEM. There we image that sample first cold, frozen state, but then we're going to heat it up inside the microscope, and then we're going to look at the restarting that process again, restarting the process that we froze in the bulk state, and now we're hoping to look at these at the restarting processes with nanometer or nanoscale resolution, as Luca already explained. So this is the big dream, so that we basically can restart frozen processes in the microscope, but now look at them live, like in a real tissue sample, look at the processes live and with nanoscale resolution. There, we will have the same challenges as we have in looking at the dynamics of liquid phase electron microscopy. So there, sparse imaging in STEM will be an important tool.